This module, the Online Training for the ODOT Analysis and Traffic Simulation, or OATS manual, provides details on the typical inputs that go into the traffic analysis for ODOT projects. ODOT preferences are described. At the end of this module, you'll be able to identify the general inputs that go into the traffic analysis, understand when the default factors should and should not be used for ODOT analysis, and differentiate between calibration and validation. Grade should be considered whenever it exceeds 3% for longer than a half mile. For most cases, the default grade should be level. For locations where the grade exceeds 3% for longer than a half mile, the actual grade should be used for the analysis. If grades cannot be field measured, they can be estimated using Google Earth. Grade for ramps shall be assumed to be 0. Traffic flow rates typically vary over the course of an hour. The peak hour factor is a measure of the traffic demand fluctuations within the analysis hour. The peak hour factor is calculated by dividing the total hourly volume by 4 times the volume during the peak 15 minutes of the peak hour. A peak hour factor of 1 indicates that the traffic volume in every 15-minute interval is the same and therefore the traffic flow is consistent throughout the hour. Peak hour factors over 0.95 are often indicative of higher traffic volumes, sometimes with capacity constraints on flow during the peak hour. Lower peak hour factor values indicate more variable traffic flows and that the traffic volume has a spike during the peak 15-minute intervals. This spike typically occurs in locations with highly peaked demands, such as schools and factories during shift changes. Peak hour factors in urban areas generally range from 0.8 to 0.98. For ODOT projects, the existing year peak hour factor should be calculated for all intersections from collected traffic counts. The peak hour factor should be calculated for the intersection as a whole and not individual approaches or movements. The minimum peak hour factor should be 0.8 unless it is justified by peak demands. The peak hour factor for the design year is assumed to be the same as the calculated peak hour factor for the existing year. For mainline freeway segments, a default peak hour factor of 0.94 should be used for all analysis. The ramp peak hour factor will be the peak hour factor calculated for the ramp terminal intersection. In the event that project-specific counts are not available, default peak hour factors of 0.94 for ramps and 0.92 for arterials should be used. For analysis conducted in HCS, the hourly volume and associated peak hour factor will be entered directly into the software. Peak hour factors are accounted for through various methods when conducting transmodeler analysis. First, the volumes could be entered in 4 15-minute periods. Secondly, after entering the hourly volumes, the appropriate peak hour factor can be entered using the turning movement table settings. Alternatively, when using origin-destination matrices, a curve-based time distribution based on the calculated peak hour factor can be created. Refer to Chapter 7 of the manual for more information. Only one peak hour factor for the entire project can be used with transmodeler software. A critical study intersection or high-volume intersection should be selected to represent the study area. If the majority of the study area is freeway, the default peak hour factor of 0.94 should be used. All peak hour factor calculations should be included in the report appendix. Saturation flow rate is the maximum number of vehicles from a lane group that can pass through the intersection during 1 hour of continuous green under the prevailing traffic and roadway conditions. Narrower travel lanes will likely provide reduced traffic flow rates. Large numbers of trucks or buses will also reduce saturation flow rates. Default saturation flow rates should be used for the analysis. For urban areas, the default saturation flow rate is 1,900 passenger cars per hour per lane, while all other areas, the default saturation flow rate is 1,750 passenger cars per hour per lane. Urban areas are defined using the Census Urban Areas Boundary Layer in the Transportation Information Mapping System, commonly called TIMS. An attribute for the UA type 10 of U indicates an urban area. Saturation flow rate is a direct input into HCS. While HCS allows for different saturation flow rates for each intersection movement, unless there is a specific reason to use different rates for different movements, which should be documented in the model documentation form, The same saturation flow rates should be used for all movements at the intersection. In Transmodeler, direct entry of the saturation flow rate is not available. Refer to section 7.3.5.2 to determine how to make the necessary model changes to reflect the field-measured saturation flow rate. When using HCS, right turns on red are not allowed, and zero value should be used for the right turn on red flow rate. At locations where right turn on red movements are a significant component for intersection operations, Transmodeler should be considered. For channelized right turn movements that are yield, controlled, or free flowing are not affected by queuing at the signal, the right turn demand should be included in the analysis. In most cases, channelized exclusive right turn lanes are not affected by queuing from the adjacent through lanes. When accounting for this demand in HCS, the unsignalized movement box should be checked and the value for unsignalized delay should be 0. If the right turning analysis is critical to the study results, Transmodeler should be used. Transmodeler can simulate right turn on red flow rates through car following and gap acceptance algorithms. However, visual inspection should be performed of the simulation to ensure the model matches existing conditions. ODOT defines a heavy vehicle as single-unit trucks, buses, RVs, and tractor-trailers, which are commonly referred to as Type B and C. The percentage of heavy vehicles represents the count of heavy vehicles that arrived during the analysis period divided by the total vehicle count for the same period. The existing heavy vehicle percentages should be calculated based on existing counts. When calculating the heavy vehicle percentages for intersections, it should be calculated by approach and not for individual movements. In almost all analysis for ODOT, the existing heavy vehicle percentages will be the same in the future. If there is a reason to believe that the heavy vehicle traffic will be increasing at a different rate than passenger cars, the future heavy vehicle traffic percentages should be calculated. For example, if a truck stop is planned within the study area, the number of trucks may increase at a different rate than passenger cars. This justification should be submitted to the ODOT project manager for approval. For HCS analysis, the heavy vehicle percentages should be calculated from the existing counts and entered directly into HCS. In Transmodeler, the vehicle fleet characteristics can be adjusted based on heavy vehicle percentages from existing counts. Refer to section 7.2.3.2 for information on how to adjust vehicle fleet characteristics. The lane utilization adjustment factor accounts for the unequal distribution of traffic among the lanes in those movement groups with more than one exclusive lane. Lane utilization factors apply at locations with dual turn lanes or where a through lane drops a short distance downstream of an intersection. Another case would be an exclusive turn lane plus a shared through and turn lane. For example, this off-ramp has a 3-lane approach with a left turn lane, a shared left turn through right turn lane, and a right turn lane. By default, HCS will view the off-ramp as a left turn lane, through lane, and right turn lane unless values are entered into the percent turns in shared lane input box. The existing lane utilization factors should be calculated from video or field observations. If the lane configurations do not change between existing and future conditions, the existing lane configurations do not change between existing and future conditions, the existing lane utilization factor can be assumed for future conditions. If one alternative changes the lane configuration such that the lanes will be more evenly utilized, the default lane utilization factors can be used for future conditions. If the future condition involves a drop lane downstream of an intersection where the existing does not, the lane utilization for future conditions should be estimated. Calculations and justifications for the lane utilization estimation should be provided to the ODOT project manager for approval. Very few projects are expected to need lane utilization factors estimated. For HCS analysis with dual lanes, the lane utilization data can be entered into the heaviest lane volume box of the detailed input data window in HCS. In cases of exclusive plus shared turn lanes, the percent of turns in the shared lane must be entered into the percent turns in shared lane box of the detailed input data window. The driver behavior parameters in Transmodeler and a properly coded roadway network will most likely reflect accurate lane utilization characteristics. Visual inspection should be performed to ensure that the simulation model matches field conditions. If the model needs to be adjusted, the lane connector connectivity bias can be modeled in Transmodeler. Refer to section 7.3.5.2 for information on how to adjust these parameters. Signal timings play a vital role in the analysis and can drastically impact intersection capacity operations. For ODOT projects, the existing signal timings should be used whenever existing signal analyses are performed. Refer to section 4.5 for more information on obtaining or measuring existing signal timings. Future year analysis should be conducted using optimized signal timings with the guidance provided in the following slides. Refer to section 6.2.2.1 for signal timing inputs in HCS and section 7.1.4.1 for Transmodeler. As part of the OATS manual, guidelines have been developed for optimizing signal timings for future year analysis. While they are just guidelines and not standards, deviations from these guidelines should be approved by ODOT on a project-by-project basis. Signal timing optimization can be performed in Synchro, HCS, or Transmodeler. However, no matter what software is used for optimization, the resulting signal timings should be entered into the software being used to conduct the traffic analysis. If the existing traffic signals are coordinated, they should be modeled as coordinated in the future year analysis. Cycle lengths in the future year analysis can differ from existing conditions, but should typically be between 60 and 120 seconds. Cycle lengths longer than 120 seconds may be required for intersections that are oversaturated. Cycle lengths at all intersections along a coordinated corridor must be the same. Half or double cycle lengths, such as having one intersection operate on a 60-second cycle length while the other signals have a cycle length of 120 seconds, is not permitted. If the intersection geometry changes between the existing and future conditions, or if the clearance intervals or minimum timings are not known, the following values should be used. Yellow clearance, 4 seconds. All red clearance, 2 seconds. Minimum green time for major street through movements, 20 seconds. Minimum green time for minor street through movements, 10 seconds. Minimum green time for protected left turn phases, 7 seconds. Alternative intersections such as single-point urban interchanges and diverging diamond interchanges can have a much wider intersection than traditional intersections. In these cases, the all-red time may need to be longer than 2 seconds to allow additional time for a vehicle to clear the intersection. The minimum green times should be extended to accommodate walk and flashing don't walk intervals if required. Refer to Chapter 1 for more information on when pedestrian timings should be included in the analysis. When pedestrian intervals are not known, assume 7 seconds for the walk interval and 10 seconds for the flashing don't walk interval. Typically, left turn phases should be leading. However, sometimes lagging left turn phases can reduce vehicle delays. The lagging left turn phase is allowed only if the opposing left turn lanes are protected only phases and the cue for the lagging left turn movement do not impact the adjacent through lane. Protected permitted left turn phases cannot be lagging due to yellow trap. Based on the manual on uniform traffic control devices, the yellow trap is a potentially adverse safety situation inherent in some signal phasing sequences involving lagging left turns in one direction. A left turning driver in the intersection waiting for gaps in oncoming traffic in order to turn left on a permissive green signal indication sees the signals change from green to yellow and mistakenly assumes that oncoming through traffic also has yellow signals at the same time and will be soon coming to a stop. This mistaken assumption traps the permissive left turner into thinking it is okay to safely complete the turn when in reality it is not safe because the opposing traffic continues to move on a green indication along with a lagging left turn and a severe crash can be the result. The operational goal for the intersection analysis is an overall intersection level of service of D or better for locations within the boundaries of a metropolitan planning organization and LOS-C or better for locations outside of an MPO boundary. Levels of service for each approach should be at E better and no individual movement should have a volume to capacity ratio greater than 0.93. In addition, the queue storage ratio from HCS analysis should be less than 1 for all movements. If the queue storage ratio goal cannot be met, Transmodeler may be needed to determine if queuing impacts upstream intersections. When evaluating optimized signal timings, the minor street will often have more delay than the major street. This is acceptable, but the volume to capacity ratio for the minor street should be checked to make sure that it is not significantly higher than the major street volume to capacity ratio. In most cases, efforts should be made to ensure that the volume to capacity ratios for the minor street are not over 1. A few minor tweaks in the signal timings can alter the volume to capacity ratios so that no movements are over volume to capacity. It is understood that for oversaturated conditions, volume to capacity ratios will be above 1 for both major and minor streets. For signal timing optimization guidance, please refer to Chapter 6 for HCS analysis and Chapter 7 for transmodeler analysis. Calibration is a process that demonstrates that the model is a reasonably accurate representation of observed conditions. For example, if traffic is observed to queue between two intersections, the analysis model should also show this queuing. The model should be calibrated by modifying the model inputs or parameters until the model matches the observed conditions. Validation is the act of proving or corroborating, usually with a second data source or data set, that the calibrated model can also provide realistic results under different input data or scenarios. When validating the model, the analyst may compare the field-measured average travel speed to the average travel speed generated by the model. The purpose of calibration and validation is to build confidence in the model as a useful predictor of operations that are likely to result from a condition that cannot be observed. For example, if an existing conditions model is properly calibrated and validated, when traffic from a large mixed-use development is added to the analysis, the results from the model are an accurate representation of operational conditions on the roadway surrounding the added development once it is constructed. Potential pitfalls of poor model development or poor calibration include, but are not limited to, discrepancies between field conditions and modeled conditions. In locations that have recently been constructed or improved, the aerial imagery used to build the model may not reflect the most recent conditions. Analysts should verify the model inputs through field reviews. Unrealistic driving behavior. Especially in transmodeler, the lane utilizations in the model may not accurately reflect field conditions. Discrepancies between field-measured traffic volumes and the amount of traffic served in the micro-simulation model. In these cases, the traffic volumes collected may represent capacity and not demand. Creation of false bottlenecks. Unrealistic driving behavior and miscoded models can create bottlenecks in the model that are not actually occurring. Unreasonable routings of vehicles through the network during dynamic assignment. When using the dynamic assignment in transmodeler, vehicles may not use the route they are using in reality. This routing could be the result of signed routes in the field or other conditions that make the route faster under real-world conditions than the modeled conditions. The formal process of calibration and validation is not required on standard type projects. However, a visual inspection or logical output check should be performed to ensure models are an accurate representation of real-world conditions. For example, from field observations, it is known that a queue from a signalized intersection regularly extends 1,000 feet from the intersection. If a visual inspection of the transmodeler simulation network or a review of the output does not show a queue length of this magnitude, the model should be tweaked to match real-world observed conditions. The measures selected for calibration and their targets for model calibration should be established based on the purpose and need of the project. The following lists provide outputs and metrics that should be used to compare against the field measurements to determine if a model is properly calibrated. Volume throughout, speed, travel time, queues. For HCS analysis, it is recommended that queue lengths be used to calibrate the analysis model. At a minimum, it is suggested that the volume throughput and speeds or travel times are used as metrics during transmodeler model calibration. Based on guidance from other states and FHWA at the time of this manual, suggested calibration items and their targets are summarized in this table. Based on the individual movement flows, the volume throughput generated by the model should be within a certain threshold. When calibrating to speeds, the link speeds from the model should be within 10 miles per hour for more than 85% of the network links. Travel times from the model should be within 1 minute of field-measured travel times for 85% of the network when field-measured travel times are less than 7 minutes. When field-measured travel times are over 7 minutes, the modeled travel time should be within 15% of the field-measured times. Model queue lengths should be within 20% of the field-measured queue lengths, and in general, when queues are formed in free flow areas in the field, the model should have queues in the same area. All of the information presented in this module are detailed in Chapter 5 of the OATS manual. It is important to remember that HCS and Transmodeler have different input requirements. Only complex type projects require a robust calibration and validation process. However, standard type projects should be reviewed for logical and reasonable results compared to field observed conditions.